All right, ladies and gentlemen, I have an assistant here. I found a volunteer, and this is a very symbolic gesture because this is my first semester in 3 years teaching, and I'm finally going to do so without a mask. So he's going to help me out here. Don't try to undo that one. Oh, there we go. And what's your name? Jacob. Jacob. Hope it's okay using your name on video. No okay. And welcome to Chem 131, and thank you for helping out. No problem. So what we're gonna, you may avail yourself of your seat. And thank you, Jacob. And we are gonna try to make chemistry relevant, which is hard, this introductory level, but I'm gonna use this video, I hope, if it goes okay. It probably won't. It's kind of seat of the pants kind of thing. But I'm hoping to use it in all my classes if I choose to come back and teach. What do you mean by that? All right, so we're going to start with a little chemistry. Makes sense. If I can find ChemDraw. And here we are. It's been a while. I want to share screen to ChemDraw. And I realize you know almost nothing about chemistry, which is cool. We call that tabula rasa, starting with a clean slate. And a common symbol you see in chemistry a lot, and I kind of got a kick out of this morning because I was checking out Joules. Remember who Joules was? It's our first quiz of the day. Who is Joules? He was that guy. He's the guy at Pearson who does videos. Okay. And on his shirt, there's this picture. Okay. And that picture is very big. Let's do a side. Sure. Okay. And what does that mean? Well, that is a molecule in organic chemistry. So not only are we talking about chemistry, which we haven't heard of before, now he's talking about organic chemistry. So let's talk about what's chemistry, period. Chemistry can be quickly defined as the study of stuff. Scientists don't like the word stuff. It doesn't make them sound erudite enough, smart enough, okay? So they use what word instead of stuff? Starts with an M. Matter. Yes, only chemistry matters. Oh, I like that one. Yeah. They all matter. So anybody have any inkling what this is? A short form representation of the molecule benzene. Have you heard of that? Good. We're not supposed to be using benzene anymore. It used to be used all the time by all chemists that were organic because it was a wonderful solvent. What do we use solvents for, everybody? Dissolving, in particular for cleaning or for running a reaction. Now, in your chemistry course that you're enrolled in, the solvent of choice every week will be water. So when we say solvent, it's generally water for you. But organic chemists, it's rarely water. Does anybody know why they would be using different solvents for organic chemistry than for other chemistry? Well, the key word you mentioned earlier, she says for dissolving stuff. Yeah, that's the whole key. Dissolving stuff. Solvents dissolve stuff. And there's this concept you're going to learn about that's very important in this class called polarity. Have you heard of that? Yeah. If you take sugar and mix it with water, it dissolves, right? If you take sand and mix it with water, does it dissolve? No. Well, we say that the sugar is soluble, means dissolves. And the sand is insoluble, doesn't dissolve. You better choose a different solvent if you want it to dissolve. And in chemistry, solubility is profound. Okay? I am an organic chemist, and my leanings are towards biochemistry. It's the chemistry of life, right? But it's just chemistry. It's no different than the other chemistry. Okay? And to me, polarity says, okay, if it's polar, you're going to need a polar solvent like water to dissolve it. And if it's non-polar, you need a non-polar solvent. Like, do you know any non-polar solvents? Oil, yeah. Paint thinners, turpentine. How many people know about turpentine anymore? Okay. Acetone, ladies, what do you use acetone as a solvent for? Nail polish remover. Yeah, it dissolves the polymer. It's called nail polish. It's an acrylic sometimes. It's other things other times. Anyway, we're going to get back to our molecule, and benzene doesn't dissolve in water. It's a great solvent for dissolving non-polar things, but it's also a carcinogen. What does that mean? Cancer causing. We didn't know that, and we lost quite a few chemists before we figured it out, which is sad. All right, so fixed length. So when we have a short form like this in chemistry, these corners are always carbons. That's a small c, isn't it? How about a big C? There we go. So I'm just filling in what that picture really is. And that's not the whole picture. Carbon is the central atom in organic chemistry. None of this stuff I'm talking about here is on any test ever. Okay? I'm previewing some things. I'll say, you're going to see this in this course, right? Or this is organic chemistry. You're not going to see this in this course, but I want you to see it's all related. That's the only purpose of this discussion. See how profoundly related to every minute of everyday chemistry is in your life, and you've been taking it for granted all these years. Wow. And carbon likes forming 4 bonds. Those sticks between carbons are bonds. You're going to learn what a bond is later this semester. Oops, sorry. My computer thinks it's smart, and it's trying to help me. So we're here so far. Carbon's nature is to form 4 bonds. You don't have to know that now. In organic chemistry, when you take it, you will. So the stick figures we saw before, which is basically here, is a short form for this molecule here. There's the 4th bond for that carbon, and it's a hydrogen. And hydrogens are allowed to be missing on stick figures clearly. So why don't I put all the bonds on first? See, me talking and doing, can't do it. I still try. Okay, so the molecule benzene in its full glory of bonds is here. And we don't like benzene, right? It's toxic. So let's make it into something we like. Benzene is part of the skeleton of a very common medicine. If I told you its name, I'm just going to do some drawing here. There's an O here. And there's a C here. And another O up here. And an O here that also has an H. No, that's not what I wanted. It has a CH3 there. This little chunk over here is called an acetyl group. Whoa, I don't know what happened there. That was weird. You probably won't see anything on the video, but something just blocked my screen. So I put an acetyl group on my benzene. And on this benzene, I'm also going to put something else. And this time that'll be hydrogen doesn't do that. Nope. Yeah. And this is the most commonly used medicine in history now. Right there. That thing I put on there is a carboxylic acid. Once again, what's he talking about? Carboxylic acid. Now, you guys haven't studied chemistry yet. We better save this day 1 lecture somewhere. But some of you have heard the word acid. No? What do you think of when you have heard the word acid? Sorry? Lemons have acid. That's right. It makes them tart. I like that taste. You like that taste? Me too. Hydraulic acid. Like for a hydraulic system? Oh, is that like a skin term? Like a skin health word? Because I'm not familiar with the combination of the hydraulic with the acid. Hyaluronic acid. Ah, that's a good one for your skin. Yeah, that's got a carboxylic acid in it attached to a glucose. Have you heard of glucose? Yeah, yeah. That's the one that's got a polymer of glucoses glued together, like a whole line of them. Anyway, we're getting a little far afield, but that's an acid, yeah. And that's good for skincare. And carboxylic acids, have you heard of pH? You vaguely, we've all at least heard the expression maybe, right? Acids tend to lower pH. You're going to learn it later. And not in great depth in this course. Acids, we can only do a little cursory talk near the end, okay? But they're very important, right? So acids lower pH, they taste tart, okay? And over here we have an ester here. You don't need to know that. Anyway, this is called acetyl salicylic acid. Acetyl salicylic acid. You ever heard of it? Maybe you've heard that name, ASA. Maybe you've heard this name. Oh, spelled wrong. Aspirin. Most commonly used medicine in the history of mankind. Yeah. You know how long we've been using it? Long time. But before we were using that, we had stuff that certain people knew more about than we did. Make that an OH there. Get rid of this. This here is called salicylic acid. What's it missing in the name? Acetyl. What's acetyl look like? Right there. Acetyl's there, and it's not here. So, not in the name anymore. Okay. Sorry. Yeah, straight up telemarketer says right there. Okay, salicylic acid. Ever heard of it? Yeah. It's good for what? Yeah, it's a good, yes, exfoliating is a way to say it, but it's really a good antibiotic. Right? You know any other antibiotics that you can rub on things? There's a real good one when you get a cut. Hydrogen peroxide's a good one. Yeah. That's for the swelling. Cortisones are powerful. They're in the steroid class. But yeah, we got salicylic acid and hydrogen peroxide. Okay? Salicylic acid, peroxide. Both good disinfectants. Hydrogen peroxide looks like this. You got an oxygen here. Whoa, I missed. Oxygen there, hydrogen here, hydrogen here. It's like water with an extra O, peroxide. Per means extra. Okay. So that's a disinfectant that works nicely on infections in your bloodstream. A cut is at the end of your bloodstream. That's why you're bleeding, right? Okay. You want to put hydrogen peroxide in that because it gets right into the bloodstream and starts killing bacteria. Okay. And that's not what the bubbles are. The bubbles are you. You've got an enzyme in your body. You ever heard of enzymes? Enzymes are machines. You don't see them. They're incredibly small. They're molecular sized machines. And if you put the right chemicals in at the right time, they do reactions. And if you put the reverse, like the product instead of the reactants, you can reverse the reaction with the same enzyme speeding it up both ways. It's all dependent on need. And this is the most fascinating thing about biochemistry to me. Your health is depending on garbage in, garbage out, and healthy in, healthy out. Okay? And it's all equilibria. These are words that you have no idea what I'm talking about. But it's all chemistry. But anyway, we got hydrogen peroxide here, good disinfectant for water-based wounds like your bloodstream. And this is for infections that are underneath some oil and grease that's trapped in your skin. You know, certain times of your life you're producing more of it. And if you're blessed like me, you get pimples even now. You know, okay, sometimes not as much as I used to, but anyway, salicylic acid will get underneath that and disinfect. And remember me talking about polarity? This looks a lot like water right here. In fact, that's hydrogen peroxide down there, and there's water up there. You can tell they have fairly similar makeups, right? And for reasons you don't know why yet, they have very similar polarities. Okay? Well, this thing, carbon and hydrogen are not, they don't make polar bonds. You don't know what that is yet, but it's all about polarity, which he told us is really important. It tells you where molecules are going to go. What's the destiny of that molecule once you ingest it? So I'm going to, ingest some acetylsalicylic acid, okay? Because I have a headache. I could have ingested salicylic acid because it also works for headaches. But because this thing irritates your stomach, everybody gets serious cramps if they ingest salicylic acid. That's when Mr. Bayer, you ever heard of him? We're talking 1800s. The German pharmaceutical, Bayer company. Yeah, it's too old. But anyway, he came along and he put the acetyl group on there. And now it's only a side effect for 2 or 3% of the people who take it, the irritated stomach. And it's nowhere near severe for anybody. So problem solved, right? Put the acetyl group, get rid of that bad effect. They both have good pain relief qualities. All right. So what's the first thing that happens when you ingest an aspirin? Well, this molecule here is not very water soluble, and you put it where? In your stomach. What's the liquid in your stomach? It's water with acid dissolved in it. But remember, it's biochemistry. That's water. Your bloodstream is water. That's the solvent of life. Got it? So this thing don't like water. It's got too many carbons and hydrogens. So it's sitting around on the top of that, on your tummy, and you're saying, well, that was not a good drug to take. It doesn't dissolve. The acid in your stomach, acids do something with molecules. They give them like a little hydrogen atom. See hydrogen up there? First element on the periodic table? Well, when it's by itself, like all by itself, it's H plus with a plus charge. That is your acid functional piece. And the acid in your stomach goes somewhere on this molecule, and it's typically here or here, but you don't need to know that. It makes a bond to those O's, and then it makes them soluble. Isn't that cool? Now aspirin's dissolved in your stomach. What's going to happen now? Where does it go? Stomach's not a destination, a final destination, is it? What's next? Well, some chemistry happens in the stomach, right? Other than just putting a hydrogen on the thing to make it soluble. There's some reactions that are starting in the stomach, like hydrolysis. That's a word that makes sense if you think about it. Hydro is water. And get used to lysis as a suffix. You're going to see it many times if you take any science classes. Lysis is cutting. Okay? Lyse, cut. Just learn that today. It's a good thing. So some of it undergoes hydrolysis to salicylic acid. Now you understand why some people have that side effect, right? Because it doesn't happen to a great extent in the stomach, but when it does, that's you're getting an irritated stomach because now you have salicylic acid after hydrolysis. The rest gets absorbed because it's still a non-polar molecule into what's after the stomach. What's next? What's next? The intestines. Yeah, I know. There's not a biology class. Stop. You don't have to know any of this. Yeah, but, okay. She went into a lot of detail. Okay. So yeah, but those intestines, they can absorb material straight through the skin layer of the inside of the intestine, and that's where we get a lot of our nutrients. Okay. So what's the fate of it after that? Most of it's still acetylsalicylic acid. Some of it's salicylic acid. It goes further on in your body, and eventually it finds itself everywhere, including the site where that pain is. Aspirin's amazing. Aspirin inhibits, remember those enzymes we talked about? What was an enzyme again? It's a little machine. It's a little factory. It makes things go fast, very efficient, highly evolved factory. Okay? So the enzyme does hydrolysis and releases some more salicylic acid, which kills pain. Okay? And this thing inhibits an enzyme called cyclooxygenase, which creates, basically, that enzyme is responsible for creating platelets, which are responsible for what? Blood clotting. So aspirin also has a side effect, right? The good blood thinner. Okay. And it stops the enzyme from making those platelet-making molecules. So your blood just doesn't clot, doesn't have the precursors to platelets yet. So you get a sense that chemistry is involved in everything you do. Just you taking notes. You're breaking down ATP so your muscles can do that and write on the page. It's like everything you do is chemistry. The actual process of vision is chemistry. Looking at you. Yeah, do you know what's going on there? I gotta stop soon because you can see I can go on for weeks. It could happen. Okay, you're hoping I do. That's less material for you to learn. Okay, but in vision, there's a molecule in your retina called retinal. It's a molecule that fits in there. It fits into an enzyme. Surprise, surprise. Okay, and it gets in there and absorbs energy from light, and it pops a bond. It pops one of these kinds of bonds. The light from what getting into your eye has energy, okay? And it's not that bond because this molecule is not a vision molecule, but it's a second bond. You see how there's two bonds between those carbons? It pops one of those. And that molecule, retinal, has got about 8 in a row. And it picks the middle one because that's the one that fits in the enzyme where the chemistry happens. It pops it, and then the carbons rotate. And now they have this shape instead of a zigzag shape. That's a different shape, right? The enzyme's got to change shape to fit the molecule now, right? Oh, this is the coolest thing. This is the coolest thing. Okay. Enzyme. What happened? When it changed shape, it hit a switch. Okay, well, the enzyme can have a little switch in there too, and that switch sends an electrical signal to the brain and literally says, I see. Isn't that cool? That's pretty cool. So I could draw retinal for you, or I could have my computer draw it, and you don't want me to draw it. Convert name to structure. And there's your retinal. And it's all stick figures and stuff. So what are the atoms that are missing in our stick figures here? No, the carbons are at the corners. I mean, they're missing. I hear you now. Okay, I hear you. But I know where the carbons are because the end of a stick is a carbon. You don't have to know this, but you know, when you get there, end of a stick's a carbon, intersection of sticks is carbons, there's your carbons. But the hydrogens are not showing at all except for this guy, or none of them are showing. You put them on when you take organic chemistry, okay? And the bond I was talking about that changes from one geometry to the other is that one right there. You want to see it happen? First of all, this binds to an enzyme in your eye called opsin by way of a nitrogen atom. So now it's a new molecule. That's not retinal anymore. It's bonded in the back of your eye to the retina and to a protein called opsin, and now it's called rhodopsin. You ever heard of a rhododendron? It's a very pretty flower, purple. Have you ever went to your eye doctor and have him take that picture of the back of your eye? What color is that retina? Deep purple. Smoke on the water, deep purple. Nobody gets that reference. It's fine. Okay? So, rhodopsin is this molecule now. Enzyme over here, connected to retinal. Now the light comes in. Want to see what happens when the light comes in? Boom. There's the new shape of the molecule. It's different than before, right? Don't believe me? Old, new. Uh-oh. I got to do it again. It's definitely a different shape, right? That's when your enzyme changed shape. That's when the signal to your brain happened saying, I see that light. And how fast is that? Thousands of times per second. Wow. Okay, if your mind's not blown now, then it's not going to be. That's okay. We're just here to get you through the basics, right? Okay, chemistry is fascinating, right? And here we go.